Welcome to our virtual classroom, students. We are jumping right in today. In this explainer, we're going to uncover the totally invisible mechanics of how sound travels through the world around us. We experience sound every single day, right? From your alarm clock in the morning to the music you listen to on the way home. But have you ever stopped to think about what sound actually is and how it physically gets from an object all the way into your ear? Well, that is exactly what we're going to unpack today.
Okay, let's set up a scenario. Imagine two astronauts doing a spacewalk, actively repairing the metal hull of a space station. They're out there working hard, and one of them is just hammering away, clanking a heavy metal wrench against the station to secure a stubborn bolt. It seems like incredibly heavy, noisy work.
So here's a question for you to hypothesize on. Can those astronauts actually hear those heavy metal impacts? If you were floating right next to them, no radio, nothing, would you hear that clanking metal just like you would down here on Earth? Hold on to your guess, because by the end of this explainer, the physics of this exact situation will be crystal clear.
To solve that mystery, here's our lesson plan for today. We'll look at 1. The origin of sound, 2. Instruments, 3. The propagation medium, 4. Wave density, and 5. Graphing the wave.
Section 1. Origin of sound. Where it begins.
Let's think about a really classic classroom activity. Imagine an empty cardboard box with a rubber band stretched tightly across the opening. When you pluck that rubber band, you can clearly see it blur as it snaps back and forth. It creates a periodic to and fro motion, which physicists call an oscillation. Now, the absolute key takeaway here is this. As long as that rubber band is moving, sound is being produced. But the very second you touch it and force that movement to stop, the sound instantly stops too. Every single sound starts with a mechanical vibration. No vibration, no sound.
Section 2. Instruments. Vibrating parts.
Think about smashing a pair of heavy brass cymbals together. Metals have a cool property called sonority, meaning when you strike them, the metal vibrates violently and it produces a loud, ringing sound. But this doesn't just apply to metal. When you speak, air from your lungs forces the vocal cords in your throat to vibrate. So your very own vocal cords act as the vibrating source of literally every spoken word.
So whenever object is producing the sound is called the source, and different sources vibrate in totally different ways. You've got striking metal objects like cymbals, vibrating strings, or vibrating membranes like the stretched skin on a tabla drum. But not all instruments even use solid visible parts. Take a flute or a bansuri, for example. When you blow into that hollow pipe, you actually aren't vibrating the wood at all. You're vibrating the actual column of air trapped inside the pipe. The air itself becomes the vibrating source.
Section 3. Propagation medium. How sound travels. To understand how the sound gets from the source to you, imagine a slinky toy. If you and a friend hold opposite ends of a stretched slinky and you give your end a sharp, quick push, a visible disturbance travels all the way down the coils. That slinky is the perfect classroom analogy for a medium. A medium is simply the physical matter or substance that sound is transmitted through. For us, sitting in a room, that medium is the air around us. The source vibrates, and it sends a disturbance through the medium, exactly like a push traveling through the metal coils of a slinky. Section 4. Wave density. Highs and lows.
Let's mentally zoom in on those air particles for a second. Imagine a piston rapidly pushing and pulling air inside a long tube. As the vibrating object pushes forward, it literally shoves the air particles in front of it closer together, squishing them into a region of high air density. Then, as the object pulls backward, it leaves behind this empty area where the air particles are all spread out, a low-density region. Because the object is vibrating back and forth incredibly fast, this cycle just repeats over and over, sending alternating regions of packed and spread out air traveling outwards.
Now, we actually have formal names for these regions. Those crowded, packed air particles, we call them compressions, and they're usually labeled with a C. These are regions of high air density and, consequently, high pressure. We contrast these with the spread-out, emptier regions called rarefactions, labeled with an R. Those are regions of low air density and low pressure. So sound is quite literally just these alternating compressions and rarefactions traveling through a medium.
Because of how this push and pull mechanism works, we call this specific type of disturbance a longitudinal wave. The air particles themselves don't move up and down like waves in an ocean. They just vibrate back and forth along the exact same path, parallel to the direction that the wave is traveling.
Bringing it back to the slinky analogy, you can clearly see this longitudinal wave happening.
The bunched up tight turns traveling down the spring, those are our compressions. The looser, spread out turns trailing right behind them, those are the rarefactions. And if you could put on magic glasses and map that onto the actual air around you, you'd see dense clusters of particles alternating with sparse, empty areas. This is the invisible reality of sound that is surrounding you right this very second. As I'm speaking to you, my vocal cords are actively pushing and pulling the air, creating these alternating density changes that are traveling steadily away from my mouth.
Section 5. Graphing the wave. Visualizing sound.
So, how do physicists actually draw these invisible clusters on paper? We graph it. We plot the density of the medium on the vertical axis and the distance from the source on the horizontal axis. The region of highest particle density, those compressions we just talked about, becomes the highest point on the graph, which we call the crest of the wave. The lowest density area, the rarefactions, drops below the average density line and becomes the lowest point on the graph, known as the trough.
And looking at this graph gives us a really important measurement, the amplitude. The amplitude of a sound wave is simply the size of this density change. It's the maximum change in the density of the air compared to the normal, everyday average density of the room you're sitting in. A larger, more forceful vibration pushes the air particles much closer together, creating a larger change in density. That means a larger amplitude and ultimately a much louder sound.
Of course, out in the real world, sound isn't just trapped inside a straight tube. A sound source constantly produces compressions and rarefactions that spread out through the surrounding air in literally all directions, creating these really beautiful, expanding spherical waves. Okay, if you take away just one single thing from this explainer, I want it to be this quote from our source material. The particles of the medium do not travel with the wave. They just vibrate about their mean positions. This is incredibly important. The actual air molecules near your computer speaker do not travel all the way across the room and fly into your ear. No way. They just bump into their immediate neighbors and bounce right back. It is only the disturbance, the wave of energy itself, that travels the distance.
Which finally brings the lesson full circle back to our spacewalking astronauts. So can they hear the metal clanking? The answer is a definitive no. Sound is a mechanical wave that absolutely requires a medium to travel through. Because outer space is a vacuum, meaning it is completely devoid of air particles, there is literally nothing for those vibrating metal tools to push against. No particles means no compressions and no rarefactions. So despite the massive, violent vibration of the metal wrench, the result is absolute, utter silence.
Amazing, right? The very air we breathe is the invisible fabric that connects our world through sound. So, as we wrap up this virtual classroom session, I want to leave you with one final thought to ponder. If sound is just physical waves of high and low pressure air spreading outwards, how might architects use the curved ceilings and walls of a massive concert hall to manipulate and bounce these compressions and rarefactions to perfectly deliver sound to your ears? Think about how those physical waves reflect. Thanks for joining me in this explainer today. Keep wondering, keep learning, and I'll see you next time.